Hey folks, in this video I will be introducing you to the concept of index of refraction. So, I want to remind you, last video we talked about light being a set of perpendicular oscillating electric and magnetic fields, and this creates what we call an electromagnetic wave. So this wave in particular we've got here propagating in the direction along the x-axis, and the electric field and magnetic field vectors are perpendicular to each other, and they are both perpendicular to the direction of propagation, which in the last video we wrote like this. Our E field, our B field, and our velocity are all perpendicular to each other. In this video, we're going to talk about that wave speed a little bit more and talk about what factors affect the wave speed. So here we have it. Like all waves, the speed of an electromagnetic wave depends only on the medium through which it's propagating. That's the only thing that affects how fast the wave is moving. And by medium, I mean for light, if our light waves are passing through water or glass or air, those are the types of mediums we'll think of when light is traveling through them. So a reminder that c is the speed of light in a vacuum. That is, in the absence of any matter, light can propagate at 300 million meters per second. However, that's the speed in a vacuum. We're going to define a new property now to figure out how fast light moves when it's in a medium. So we're going to define this new property. It's called index of refraction. And its definition is going to be the ratio of light's speed in a vacuum compared to light's speed in some medium. So here is that quantity, index of refraction. We're going to use n as our index of refraction, and v here is the speed of light in a medium. It's always slower than the speed of light in a vacuum. It's never faster. N is this new quantity, index of refraction. And so there we have it. That's our definition. Since the speed of light is always fastest in a vacuum, that means the denominator v is always smaller than the numerator c, and our indices of refraction will always be greater than or equal to 1. Here is a table with some common indices of refraction. By the way, that is the plural of index. It's not indexes, it's indices. Feel free to say either. But here we go. We've got a whole table here. We can see that in a vacuum, light moves at 300 million meters per second. Its index of refraction is 1.0000000 forever. In air, to 3 significant figures, light also travels at 300 million meters per second because the index of refraction for air is actually 1.00029. And so it's only at greater significant digits where we see deviations in the speed of light from what it is in a vacuum when it's in air. Moving down, when light is moving through water, it only moves at a speed of 2.25 times 10 to the 8 meters per second. And if you take the ratio of c divided by 2.25 times 10 to the 8 meters per second, you end up with the ratio of 1.33. So that's our index of refraction for water. Got some other solutions here. Glass, we can see, has an index of refraction of around 1.5, sometimes 1.6, depending on the glass. So you get a range of speeds for glass. And then for diamond, which has a very high index of refraction at 2.417, light moves very slowly through diamond at 1.24 times 10 to the 8 meters per second. Of course, slow relative to light, right? It is still in over 100 million meters each second. I want to point out that the index of refraction is a dimensionless quantity. It's a ratio of 2 speeds, and so there is actually no unit or dimension to it. And we want to talk about, why does light slow down rather than speed up in a medium? Well, light slows down because the electric fields of the light wave interact with the electric field of the matter that's already there, right? Matter is made up of charged particles, protons and electrons, and the interaction between the incoming electromagnetic wave and the positive and negative charges of that medium slow it down. And I already mentioned this, but since the speed in a material is always less than or equal to the speed in the vacuum, n is greater than or equal to 1 always. We like to think about this index of refraction quantity, if you're trying to wrap your mind around it, as optical density. The bigger that number is, the more dense it is for light to move through, and the slower light's going to go. So it's our density for optical things, for light. The higher the number, the slower light moves through it. Now, here's an idea we need to wrap our mind around. When light enters a new medium, the frequency of the light wave must remain the same. When light enters a new medium, the frequency of the light wave must remain the same. Let's think about why. It's an idea of continuity, of when, here we see this picture here, we've got an incoming light wave. It's in medium 1, which is a vacuum, index of refraction 1, that enters a material who is 3 times as optically dense as medium 1. Medium 2's index of refraction is 3 relative to medium 1's 1.0 index of refraction. And we have this continuity idea that the waves entering at this boundary per second must be the same number as the waves that are leaving each second, right? The amount of wave isn't changing each second. Waves per second, that's frequency. And so when we're entering a slower medium, the wavelength must decrease. In order to both slow down and keep the same number of waves per second, those waves get bunched up. We have the same number of waves per second, the same frequency, but we slow down, we have a slower wave speed. So the wave crests get bunched up as a result of the incoming waves slowing down. So we get a lower wavelength. We can also think about this through the lens of our wave speed equation. Speed is wavelength times frequency. In this case, the frequency is what is constant across our media. Incoming waves per second equal outgoing waves per second. And as a consequence, if we decrease the speed, we must also decrease the wavelength. We have a direct relationship between the two there. If we enter a faster medium, the wavelength increases, right? The reverse is true. If we get faster, then the waves will get more spread out because we're not getting any more waves per second. And so if our speed goes up, our wavelength must also go up. There's that direct relationship again when the frequency is constant. When is the frequency constant? The frequency is constant whenever we're changing mediums. Be careful. This is a place where students make some mistakes pretty frequently. When using speed as wavelength times frequency and you're doing some proportional reasoning, sometimes speed is constant, sometimes frequency is constant. So different variables are constant under different conditions. When your medium is not changing, if we're just staying in a vacuum or in air or in glass or in water, then it's the speed v that is constant. When that happens, there's an inverse relationship between the wavelength lambda and the frequency f. So looking at our equation, v is constant within a medium. So as frequency goes up, wavelength must go down in order to keep v the same. Or if frequency goes down, wavelength must go up again to keep the speed overall the same. Making one bigger, the other gets smaller to keep the speed constant. If you're transitioning from one medium to the other, on the other hand, which is what we just described on the previous slide, frequency f is what is constant, and then we have a direct relationship between wavelength and frequency. So same equation, but now it's f that's constant. So a decreasing speed means a decreasing wavelength, and an increasing speed means an increasing wavelength. So all the information you need is there, but you need to keep in mind what is constant under what conditions. Same medium is same speed. Transitioning from one medium to another is same frequency with different speeds. That's the end of this slide. That's our introduction to the concept of index of refraction, which is our optical density and tells us how much light will slow down when it enters the medium.